Just like a 45 nanometer technology node is fine forever out into the future, which brings our costs way down relative to competitors like NVIDIA. So here's the full fabrication stack that we're building towards, where we combine semiconductors, superconductors, and photonics. We think it makes sense to start with CMOS. That provides control bias circuitry. So we take a 300 millimeter wafer, do a conventional CMOS process. It doesn't need to be state of the art. Just like a 45 nanometer technology node is fine forever out into the future, which brings our costs way down relative to competitors like NVIDIA. And then on top of that, we do these repeating modules that have photonic routing waveguides with single photon detectors, inductive wiring for these integration loops, and Josephson junctions. And these modules can actually be repeated. So one of the huge advantages of superconductors over semiconductors is that based on all the various process considerations, you can put multiple planes of actives. So in CMOS, once you put down your transistors, you do your ion implantation, your activation anneals to drive in the dopants. That's at like 1100 C. And then you do your wiring layers and anneal those for metal semiconductor contacts at 600 C. You can't do that again because you can't go put another layer of transistors and anneal for the dopant activation, at least not for a logic process. And you can do some 3D memory, of course. That flash and 3D flash has come a long way. But that's very different than the compute circuitry, which is very hard to do in 3 dimensions. And even if you could, the power density becomes so high that it's really not a viable approach. And it has been pursued for decades, but nobody's really doing it these days. With superconductors, that's not the case. You can put multiple planes of Josephson junctions. It's been done by Lincoln Lab and also by a group in Japan, I believe at the Gravity clean room there. And the power density, especially in this AI application where activations are sparse, activity is sparse, most Josephson junctions are not switching at any given time. So the power density stays very low, and you can easily extract all the heat through the top and bottom of the wafer using liquid helium. So we think it's extreme scaling advantage. Even though JJ circuits are bigger, we can get close to the same density as a semiconductor neuromorphic approach by using this 3-dimensional scaling.